Hi, welcome to es301 Engineering Analysis. This is chapter 14 on multi-dimensional unconstrained optimization. So here are the learning goals of this video. At the end, you'll know the difference between the gradient and the non-gradient methods. They're also called the direct and ascent methods for optimization. You'll understand how the univariate search algorithm works and why it's not particularly efficient. You'll know what a Hessian is and how to use it to determine the minimum, the maximum, or the saddle point of a multidimensional system. You'll know how the steepest ascent method is implemented. Within that, we'll be able to convert a function that's of x and y into a function of h, so turning something that's a function of two variables into a function of one. And we'll recognize Newton's method is implemented for multidimensional searches. So a lot of learning goals in this video. So first, let's discuss multi-dimensional optimization sort of in context of what we looked at before, which was one-dimensional optimization. So we're looking for a point where a function is a maximum. So here I have a function of two variables. It's a function of x and y. And so clearly, if I was to plot a surface plot, what I realize is the maximum is at this point right up here at the top. So that's what I'm trying to find. But when we're doing this numerically, we can't see this whole field. And so what we do is we start at some arbitrary point. And then what we do is we have to go search for this. We have to essentially start walking around to go ahead and find where it is. Now, one of the things about the function that I show here, notice this has what's called a global maximum, which is this point right up here at the very top, because that's the maximum everywhere. But I also have a series of what would be called local maxima, which are all these points right around here. If you were to walk up to that point, up on a sort of this lower ridge, you wouldn't be able to go anywhere that didn't involve going down further. So you would feel like you're at a maximum, and sometimes it's hard to find a global maximum when there's a local maximum, because numerically you don't know that you need to continue looking elsewhere. Again, you can't see this whole surface numerically. Multi-dimensional systems are a little bit hard to visualize. A lot of times we like to look at these in a two-dimensional sense, and so if I was to go ahead and look straight down at this, I would draw a contour map. So we'll be using contour maps a lot. And so what I'm going to do now is essentially just go ahead and take lines at every given elevation increment, so maybe every 10 meters or something, draw a line there, and then I'm going to go ahead and cast those on two dimensions. So where things are very steep, the lines tend to be fairly close together, and then where they're not very steep, they tend to be further apart. And you'd have a contour map that looks this way. Now, one of the things when you lose this level of dimension is you can't tell what goes up and goes down, so often you want to go ahead and mark or label what these contours are so you know if you're going up or if you're going down. Now, looking for the maximum, now one option is kind of the brute force method, is just to randomly start shooting and calculating what your values of f are and hope that you figure out what the maximum value is, holding into what the current one is. It's not a very efficient scheme, but it's fairly straightforward. All you need to be able to do is evaluate what that function is. Just a little bit about maps. When you look at these, it's good to remember kind of the general what a topo map looks like. You're probably familiar with something like this, where the lines are very close together, like right down in here. We realize that it's very steep. You have to look at the labels to know whether which direction is going up and which direction is going down. And then areas where they are fairly far apart, then they tend to be not very steep. And then you see regions like I have indicated right here, which are kind of called saddle points or valleys, depending on whether you're going up or going down as you approach that point. And we'll be kind of addressing all of these in a numerical sense as we move through here. So first I want to talk about univariate search. So after random search, this is the next most easy to implement. So what I'm showing here is a contour map. The contour map's a little simpler. This is one from the textbook. And so what I'm looking for is this point right in the middle here, which would be either a maximum or a minimum, depending on what I'm going up or going down. And all the things we mentioned, finding maximum and minima, the steps are always the same. It's just a matter of whether you arrive at a large value or a small value in the end. What you do if you start at some arbitrary point, like this point run right over here, I'm going to have a value of that, so I'll call that the value of f at x and y. And then what I'm going to do is I'm just going to move in one direction. So effectively, I'm just going to go ahead and increase f. And so what I'm going to go ahead and do is evaluate the function at x plus some small value delta x. So I'll go ahead and keep y constant. I'll go ahead and compare that with the value that I evaluated at f of x, y. Now, if I'm looking for an optimum and this left-hand side is larger, that means I'm going up, which is in the correct direction. So what I'm going to do is I'm just going to keep increasing delta x, and each time evaluate this at another step and determine whether my new little increment I continue to increase. Now at some point I'm going to reach sort of like the edge of the ridge where it's going to begin to go down, and I'm going to go ahead and want to stop that. And then what I want to start doing is evaluating this point at x and y plus delta y. And then again, I'm going to compare that with the function at x, y. And these are new values of x and y, so I'm just call them x prime, y prime, because I'm now over here at point 2. If it's increasing, I'm going to keep going, increasing delta y, and move up again until I hit a ridge. And then I'm just going to go ahead and reiterate that. So it's fairly simple to implement. Just make little small steps each time and just walk in one direction and walk in the next direction. It tends not to be particularly efficient, particularly as you're kind of traversing along a ridge. As you get closer and closer, you do more and more little teeny steps and keep having to stop. But eventually you will reach the maximum. So again, as we often see with numerical methods, those that are easy to implement converge the slowest. And so if we want to go get something that converges faster, normally we need to introduce some additional complexity. And that's what we'll do, look at the next couple methods. So first I want to introduce this concept of the Hessian. It's going to come up a little bit. First of all, if I have a two-dimensional graph like I show over here on the right, I can have what's called a saddle point, which means it looks like a maximum if I'm looking at it in this direction. It looks like a minimum if I'm looking at it in that direction. So it's kind of both a maximum and a minimum at the same point. It's often called a saddle point, and in the picture you can tell it looks like the saddle. And so analogous to when we want to determine an optimum of a maximum or a minimum in one dimension, when we go ahead and find whether it's set the derivative to 0 and evaluate the second order derivative. And then if at an inflection point, again, we could go ahead and determine if the second order derivative is 0. We can do something similar, but now in two dimensions using what's called the Hessian. Here's the equation for the Hessian. It involves some second order differentials, but we've got a cross term over here of d squared f dx dy squared. Just to let you know where this comes from, it kind of makes some sense if you look at what the definition is. What this is the determinant of this matrix here, d squared f dx squared in the upper left, d squared f dy squared in the lower right. Cross terms on the off diagonals. These two terms are going to be equal as long as it's a continuous function. Normally in engineering we're dealing with continuous functions, so it tends to end up being, those terms end up being equal to 0. The order of differentiation doesn't matter. And so if I go ahead and determine the determinant of this, I end up with the value of what is called the Hessian. And the reason the Hessian is nice is because the Hessian tells you whether you've got a maximum or a minimum or whether you've got a saddle point. If the Hessian is less than 0, what it means is that you have a saddle point. And so we can go ahead and let's just look at kind of an example of this. Let's look at this function here, which is actually what I have plotted in the picture. X minus 1 squared minus this quantity y plus 2 squared. And what we'll do is we'll go ahead and compute the Hessian for this. And so if I want to know d squared f dx squared, well, what I need to do is take d dx of the derivative of that, of ddx, and so that right there would be 2 times x minus 1. And if I do the derivative of this right over here, that is simply equal to 2. So now let's find d squared f dy squared. So d squared f dy squared is going to end up being equal minus right over here, and then I've got a 2y plus 2. And then I'm going to do d dy of that, and d dy of that ends up being equal to minus 2. And so then the last thing I need are the off-diagonal terms, which is d squared f dx dy. So I can go ahead and start with either one of these that I just had and take the derivative of it. And so let's just take the first one and do dy of that term right over there. And what I find out is that right there is just going to be equal to 0 because there's no y's in that equation. Likewise, if I did ddx of this one over here, there's no x's, that would also be equal to 0. So now I've got the Hessian, and I just need to go ahead and put my values of 2, minus 2, 0 on those diagonals and find out what my determinant is. And so what I find out is the determinant of this right over here is just going to end up being equal to minus 4, 2 times minus 2, which tells me that I've got a saddle point in this function here. So that's one way to go ahead and use the Hessian to determine if a function is a minimum, a maximum, or if it has a saddle point. So now let's go ahead and we're going to get into some of these numerical methods to kind of talk about gradients in 2 dimensions. And the gradients is the same as a slope. So here I have a one-dimensional plot, right? We can define the slope at that point or the slope at that point, which is just kind of a one-dimensional derivative. If I have a two-dimensional plot, what we're going to do is we're going to have a gradient, but now it's going to have 2 components to it, which means the direction. So it's more or less, how does my function change as I go in a particular direction, as we show in this diagram here in the book. Again, if we have this, let's just assume this is a maximum for now. So we're looking downhill, and we can find if we go in this direction, we're going to be going down at a particular rate. And so what we often want to do is we want to take this two-dimensional plot, which maybe we think of as f of x, y, and go ahead and just look at this line, which I'm going to call that function g, and we'll call it g of h to stick with the notation of the book, where h is my distance along this little line right along here as I go. And so what that means then, therefore, is that the gradient, which is g prime at h, is going to be equal to, well, it's going to be the partial derivative of f with x times cosine of this angle that I have right here, df dy times sine of that angle that I have right over on the right-hand side. And so this will go ahead and tell me the rate at which I am going down, and that's what's called the gradient. Now, often if I'm trying to go ahead and go up or go down, what I want to do is I want to do either to go up would be the steepest descent, or going down would be the steepest descent. And what I want to do means I just want to go in the gradient direction. So at any particular point, the steepest way to go is going to be df dx in the I direction, which is the same as x as I have over here, df dy in the j direction, or the y direction. And so this right over here, del f, is the direction of the steepest ascent or steepest descent. So what I'm more or less is looking at this point here, right? I'm going to have a gradient in all sort of directions. And if I wanted to go find my maximum, what I want to do is go in the steepest direction, which would be there. And this is my equation. I took the first order partial derivatives. This tells me how far to move in the x direction, and this over here in the y direction. Okay, so let's go ahead and do an example here with the steepest ascent method. And so here I have this function, x squared plus xy plus y squared, and I have a contour map over here on the left, and then what I have is a plot over here on the right. And so let's go ahead and imagine that we're at some point, say I'm at this point right over here, which we'll do it at point 1, 1. xy is 1, 1. And what I want to do is I want to go ahead and find the maximum, which means I want to go uphill. So I'm like over here, and I want to go uphill at the fastest rate. So what I do is I'm going to take my partial derivatives, df dx, and so df dx over here is going to be 2x plus y. And then I need df dy, excuse me, go ahead and find out what that component is, and that's just going to be x plus 2y. And let's go ahead and look at, first of all, let's go ahead and find out what would be our gradient. Let's say we just want to go straight to the right. And so if we're going to go straight to the right from point 1, 1, we're going to be going in the direction of 1i plus 0j. And so that would be the direction. And so then more effect, my angle theta would just be, right, the angle theta is going to be equal to 0 degrees. And so now if I want to go ahead and look at what g prime is, so g prime of h, the gradient in the direction that I have of this little arrow, I've got df dx, which is 2x plus y, and that's times cosine of theta. And theta is 0, so this value right over here is just going to be equal to 1. And then plus df dy, which is x plus 2y. But that's going to be times the sine of theta, theta being equal to 0. That right there is going to be equal to 0. So now let's put in our value of 1, 1 into here. So I have 2 times 1 plus 1, which means that we're going to get that right there is going to be equal to 3. So that says if I was to go straight to the right, I would be going up at a rate of 3. Right. Now, what would be the steepest direction? Well, the steepest direction, which would probably be, you can kind of see graphically, must be in that point right there, is going to be equal to del f, which is the gradient. So that's just going to be df dx and df dy in the x and y direction, and we're going to evaluate that at 1, 1. So what that would end up being equal is to 3i plus 3j, which tells me that theta is equal to 45 degrees, or pi over 4, effectively. I'm just going up and to the right, it's the same right. So let's go ahead and calculate what our g prime would be. And so now what I'm going to be doing is I'm going to be putting, the only thing that's changing is I'm putting in theta equal to 45 degrees. And if I was to calculate that, g prime is equal to 4.2426. And so I'd be going up at a rate of 4.2426, which is clearly larger than 3. So that tells me that right there is the greatest rate for which to go up. So it's how to go ahead and compute the gradient, and then to compute the maximum gradient, which is what the steepest ascent method would use. So let's go ahead and implement this now for a slightly different function. I'm going to show you how the search algorithm would go. So what we're going to do is we're going to start over here at this point that I have indicated up here on there. This is actually an example from the textbook too. This is point minus 1, 1. And I have a plot here. So I'm at that point, and I want to go upward the fastest way. So you can kind of see graphically which direction we're going to go, but let's go and do it numerically. So first what we need to do is calculate our partial derivatives. So df dx, got a slightly different function this time. That is going to be equal to 2y plus 2 minus 2x. Right there is df dx. And then I also need to calculate df dy, because this is my gradient term that I'm calculating. That is 2x minus 4y. And then I'm going to evaluate it at minus 1, 1. So if I put those values in there, that's equal to 6. And this right over here is equal to minus 6. So that tells me that my gradient is 6i minus 6j. So it's also at sort of a 45-degree angle. And so now let's look at how far we want to go. Because what we want to do is we want to effectively go up to that ridge point there. So what we want to do now is express this function of x and y as a function of just this variable, the distance we're going. So it should be g of h, is the user notation of the book. So what we're doing is we're evaluating it at x plus, well, df dx times some amount h that we're going. And then I want to evaluate that at y plus df dy times some amount h. And I'm trying to determine what this amount of h is that I want to go. Well, first I'm going to go ahead and plug this. Okay, these terms here, I've got x plus this term. I've got my df dx and df dy terms into my value of f, and I'm going to get a function g of h. There's a couple intermediate steps in the book if you want to look at that. What this comes out to be is minus 180 h squared plus 72h minus 7. So this right over here is the function, this line that's going in the gradient direction, which is this value of g. Okay. So what we want to do now is I want to determine how far to go. And so here I've got my value of g. And so how far am I going to go along that? Well, what I'm going to do is I'm going to go until the derivative of this little one-dimensional line is equal to 0. So what I want is g prime. I'm going to set that equal to 0. And so what's g prime? So this is the g of h. So this right over here is going to be minus 360h plus 72. And if I set that equal to 0 and solve for h, I find that h is 0.2. So that means I want to go 0.2h in that direction right at that point. And we saw that our remember it was 6 minus 6, and so that means how far I'm going to go is going to be 1.2i minus 1.2j. So I'm going to go and go from my point minus 1, 1. I'm going to move this far. I'm going to move a 1.2 in each direction. And then I'm going to go ahead and stop because that derivative is going to be 0. And I'm going to go ahead and repeat that step, and hopefully I'm going to be going in that direction at this point. And so what I'm going to be is right there on the edge of the ridge, and then I'm going to go ahead and turn and do all of those steps again. And I'm going to keep doing that until I end up being at my maximum point. All right. So the last thing I want to do is mention Newton's method. And Newton's method is a little different. It's the same idea that we had in the one-dimensional sense. So if I had a one-dimensional function, what I would do is I'd take a single point, I go ahead and take my derivative, and I go ahead and move in that direction. Well, now we're in 2 dimensions, so what we're going to be doing is we're going to be taking some point, we're going to be finding the gradient, and we're going to step up, and then we're going to reevaluate our function at that point. So here's the equation that we use. Our new value of x that we do, we're going to have our starting point, which is x of I, and then we're going to be moving in the gradient direction, but we do this right over here where we've got the inverse of the Hessian. So first of all, we need to go and determine what the inverse of the Hessian is. So we found df dx before, now we need to find the second order derivative. So for example, d squared f dx squared. And if I go and do that, if you look at the previous slide, if I kind of back here, there's df dx, and here's df dy. So I'm going to be taking second order derivatives of those. So then I've got my second order derivative, which is d squared f dy squared. And that right there is going to be minus 4. And then my cross term, which is d squared f dx dy. And that term right over there is going to be equal to 2. So we look at what our Hessian is. Okay, our Hessian of these second order derivatives is minus 2, 2, 2, minus 4. And now I need to determine the inverse of that. So maybe we'll go ahead and put this into MATLAB and say what's the inverse of h. And it's going to go ahead and tell me that the inverse of h is equal to this, which is minus 1 minus 1 half, minus 1 half, minus 1 half, 1 half there. So that's the inverse. If I multiply h by h minus 1, I get an identity matrix. So here's the step that I want to go. I want to move in my del f direction. I'm going to go ahead and find out what my new value of x is. And so this right over here, if I was to do it, I start at minus 1, 1. And then what I'm going to go ahead and do is I've got my inverse of my Hessian. So I'm going to multiply minus 1, minus 1 half, minus 1 half, minus 1 half. And then I'm multiplying that by my gradient term. We saw the gradient before was 6 minus 6. And so now if I multiply these terms out, go ahead and figure what my new direction is. I'm going to find out that is minus 3, 0. That's how far I'm going to go ahead and move. And so what I'm going to be moving is the minus 3, 0, moving up in that direction here. And so then I'm going to go ahead and implement that step once again. One of the things you notice is I move slightly different in Newton. You're actually moving faster towards your optimum in the Newton method. Again, this can be non-convergent. We've seen that before with one-dimensional functions. Anytime you only have one point, you have the danger of it being non-convergent. So if we just review what we talked about here, we've talked about a lot of things. We saw that multi-dimensional optimization can be difficult to visualize, but all the steps that we do are analogous to one-dimensional optimization. All the different methods we looked at more or less involve walking uphill or downhill, depending whether you're optimizing, find a maximum or a minimum, and then adjusting each step. So you take a step and then evaluate which further to go. We looked at the univariate search. That was easiest. We walked in the x direction, y direction, x direction, y direction. It's the slowest converge, fairly easy to implement. No Hessians to compute. Steepest descent method is faster. It's a little bit more intensive because we have to compute this Hessian matrix. And then we also saw that Newton's method is fastest, but now we have to go ahead and find the inverse of the Hessian method, matrix. That's the most intensive, but it's going to also converge the fastest.